Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. You are here now, settling into a moment that asks nothing of you, a moment where your breath can soften and your thoughts can stretch out gently like starlight fading across a quiet horizon. And as you rest, you begin to drift into the vastness beyond our sun, a vastness filled with hidden worlds, worlds that circle distant stars, worlds that never knew the warmth of our daylight, worlds that move in silence through a galaxy so enormous that even imagination must slow down to match its scale. The space between stars is calm, far more calm than anything we know on Earth. It is a stillness that spans trillions of miles, a stillness so wide and so deep that motion feels like drifting, a gentle gliding instead of a journey, a quiet surrender to gravity's soft guidance. In this stillness, your mind begins to open to the idea that planets are everywhere. Not rare, not exceptional, but woven through the galaxy the way droplets form on a cooling window pane. One here, another there, some small, some immense, some gentle, some unimaginably harsh, and some that may hold oceans, skies, and chemical stories still waiting to unfold. Our own solar system once felt complete. For a long time, humans believed the sun and its planets were unique, a solitary family in a silent neighborhood. But as our telescopes improved, as our methods sharpened, and as our curiosity pushed outward, we learned that the galaxy is not quiet at all. It is filled with planetary systems, billions upon billions of them, each one sculpted by physics, by gravity, by time that stretches across ages longer than life on Earth has ever known. This truth changes something inside us. It reminds us that the universe is not empty. It is abundant, it is generous, it is patient, and it invites us to look outward with calm wonder, because the worlds we cannot see directly still exist, still circle their stars, still breathe in the language of temperature, chemistry, and slow rotation. Tonight, you drift among them, not as an explorer who must strain to understand, but as a quiet observer, floating through the soft darkness, simply watching, simply noticing, as worlds pass gently beneath you. You do not need to imagine noise, or speed, or urgency, because real space offers none of these. The vacuum between stars removes all sound, leaving only the faint shine of distant suns, and the delicate arcs of orbits that unfold at a pace slower than dreams. As you drift farther from the familiar glow of our sun, you begin to see the Milky Way not as a band of light, but as a map of possibilities. Each point of light that reaches your eyes tonight may hold planets, more than one, perhaps entire families of them. Some will be small and rocky, some will be warm and cloud-covered, some will circle close to their stars, glowing like embers, and some will wander alone between star systems, silent, cold, and free from any sun at all. But even the harshest world can be contemplated gently, because at this distance, every extreme becomes a slow phenomenon, a geological whisper rather than a storm, a distant shimmer rather than a violent eruption. The molten face of a lava planet becomes a soft red glow, the icy crust of a frozen giant becomes a pale, peaceful shell. The gas layers of a super-Earth swirl in broad, unhurried patterns. Everything slows down when viewed from afar. Everything becomes a quiet study of physics performing its ancient routines. And so your mind drifts, carried by this quiet tide, into regions of space where no spacecraft has ever traveled, into systems that orbit stars older and younger than our own, into clusters where planets form in the shadow of stellar nurseries, and into lonely corners of the galaxy where a single star shines with a gentle, enduring light. The unknown is not frightening here. It is soothing, because the universe keeps its distance, allowing you to observe without urgency, allowing you to rest while thinking about worlds that will remain untouched for millennia. Curiosity, in this space, is not sharp or urgent. It is soft, it is calm, it drifts the way dust drifts through a beam of sunlight, slowly, quietly, with no effort at all. As you rest, you feel the solar system receding behind you, the bright dots of the planets becoming smaller, their orbits becoming delicate rings of pale light, until even they fade into the background glow of the Milky Way. You are now carried entirely by the quiet, moving beyond the familiar and into the gentle unknown, a place where distance loses meaning and time becomes a soft, continuous motion. The stars ahead of you do not rush closer. They brighten slowly, as though acknowledging your arrival, each one a sun with its own gravitational embrace, its own stories, its own hidden companions circling in vast, slow arcs. In this drifting state, you feel no need to predict what lies on those worlds, no need to imagine life or landscapes or skies, only the comfort of knowing they exist. Steady, enduring, following their paths with cosmic patience. And within that patience, you feel your own breath slowing, matching the rhythm of worlds that take many Earth years to orbit their suns, matching the calm constancy of planets that turn so slowly that a single day may stretch across months. The universe invites you to adopt its pace, a pace measured not in minutes or hours, but in cycles of starlight, in the quiet turning of worlds we may never see directly, but can still imagine with gentle accuracy. As the galaxy expands around you, as light from billions of stars drifts across the darkness, you sense that you are gliding into a deeper stillness, one that holds both scientific truth and quiet mystery, one where knowledge and calm exist side by side, neither trying to overpower the other. This is the space where sleep can begin, not as an escape, but as a gentle continuation of curiosity, a place where thoughts can wander lightly, where the mind can drift without direction, as though it too is an exoplanet, circling within a wide, quiet universe. And so you rest here in this calm, in this drift, in this soft awareness of worlds beyond our sun, each one wrapped in darkness, each one following its own patient path, each one a reminder that the universe is larger, gentler, and more abundant than we often remember. The night grows quieter still, your thoughts loosen, and the hidden worlds of the galaxy begin to fold around you, offering a peaceful place to drift, as you float in the soft vastness of other worlds. Imagine yourself drifting in the dark between stars, not rushing, not straining, simply floating in a slow, stable orbit around a distant sun. From this quiet vantage point, you cannot see the planets directly. They are too small, too faint, their light drowned in the overwhelming glare of their star. Yet with patience, with careful measurements, with instruments designed to notice the tiniest changes, you can still know that the planets are there. Humanity lives very far from nearly all of the worlds it has discovered, and yet we have learned to sense them, not by looking at them directly, but by watching what they do to the light of their stars, watching how they tug, how they dim, how they change the spectrum of starlight in ways that cannot be explained by the star alone. We discover hidden worlds by listening to the quiet whispers of physics, by paying attention to details so small that a casual glance would never notice them. The most fruitful way we have learned to sense exoplanets is by watching for tiny eclipses, small, regular dips in a star's brightness caused by a planet passing in front of it. This is called the transit method. Picture a distant star as a perfect glowing disk of light. Now imagine a small, dark circle, a planet, moving across that disk from our point of view. For a short time, the planet partially blocks the light. Only a fraction of the star's surface is covered, but even that fraction is enough. The amount of light we see from the star decreases, not by half, not even by a tenth, but often by a few parts in 1,000, or even a few parts in 10,000, a drop so small that human eyes cannot perceive it, yet sensitive detectors can measure it with calm precision. This tiny decrease in brightness traces out a smooth curve, a gentle dip in a graph of light versus time. The planet begins to cross the star, the light starts to fall, reaches a minimum when the planet is entirely silhouetted in front of the star, and then rises back to normal as the planet moves away. By watching this dip carefully, astronomers can learn a surprising amount. The depth of the dip tells us how large the planet is compared to its star. A deeper dip means the planet blocks a larger fraction of the star's surface. From this ratio, we can estimate the planet's radius, the duration of the transit, the time between the light beginning to dim and returning to normal, tells us about the planet's orbit, how quickly it moves, how large its orbit is, along with information about the size of the star itself. And if the transit happens again with the same timing, the same depth, the same shape, we know that we are not looking at some random fluctuation. We are watching a world completing its orbit, passing in front of its star over and over again, with the steady rhythm of celestial mechanics. Instruments like the Kepler Space Telescope and the transiting Exoplanet Survey satellite have spent many years simply staring at fields of stars, hardly blinking, taking measurement after measurement, night after night, month after month. Their work is almost meditative. They do not chase comets, they do not dart from one object to another. Instead, they watch patiently, looking for these almost imperceptible dips in brightness, collecting light curves for hundreds of thousands of stars at once. Most of the time, stars keep shining steadily. Small variations appear and disappear, but nothing repeats in a way that suggests a planet. And then, every so often, a regular pattern emerges. Every few days or every few weeks, the brightness drops by the same small amount, for the same amount of time, with the same smooth, rounded shape. The data traces out a repeating pattern, a signature of a planet crossing its star, like a regular heartbeat in the light. From these patterns, over many years, we have learned that planets are not rare. They are almost inevitable, forming naturally from the disks of gas and dust that surround young stars, coalescing, migrating, settling into orbits that can be sensed from far away, if one has the patience to watch. But transits are only one way that hidden worlds reveal themselves. There is another subtle signal, a quiet gravitational conversation between a planet and its star. A planet does not truly orbit a motionless star. Instead, both the planet and the star orbit a shared center of mass, a point in space determined by their relative masses and distances. For a small planet around a massive star, this center is deep within the star, but not exactly at its center. As the planet moves along its orbit, the star also moves slightly, tracing a small orbit of its own, a gentle wobble in space. We cannot track this motion directly for distant stars, but we can sense its effect on starlight because of a principle called the Doppler effect. When the star moves toward us, the waves of light it emits are slightly compressed. Shifts in the spacing of these waves change the color of the light very slightly, pushing spectral lines a bit toward the blue side of the spectrum. When the star moves away from us, the opposite happens. The light waves are stretched. The spectral lines slide gently toward the red. By spreading the starlight into its spectrum and measuring the positions of these delicate lines with extremely high precision, astronomers can detect the star's small motion toward and away from us over time. If this motion follows a regular pattern, a repeating cycle of approaching and receding, it reveals the presence of an orbiting companion, usually a planet. This is the radial velocity method. Radial because the motion is along the line connecting us and the star. Velocity because we measure speed from the shift in the spectral lines. From the amplitude of this motion, we can estimate the planet's mass, or more accurately, a lower limit on its mass. A more massive planet pulls the star more strongly, producing a larger wobble. When we combine this information with a transit detection, we gain both the planet's radius and its mass. From these, we can estimate its bulk density and begin to guess whether it is a rocky planet like Earth, a gas giant like Jupiter, or something in between. These methods do not show us pictures of the planets. They show us patterns in light and motion, repetitions in brightness, tiny shifts in spectral lines. Yet each pattern, each wobble, each dimming and brightening corresponds to a real world with gravity, temperature, chemistry, and a long history of formation and change. In some rare cases, we can actually see exoplanets directly. This is called direct imaging, and it is one of the most delicate forms of astronomical observation. Imagine trying to photograph a small, faint firefly hovering next to a searchlight from many kilometers away. The brightness difference is enormous. The glare from the searchlight overwhelms everything. Stars are like that searchlight. Planets are like the firefly. To see the planets, we need to block the star's light without blocking the planets as well. Astronomers use devices called coronagraphs, which carefully shape and block the light inside a telescope. suppressing the star's glare so that any faint companions nearby might appear. They also imagine large structures called star shades, flying in space far from a telescope, aligned with incredible precision, so that the star's light is blocked before it even enters the telescope, leaving only the dim glow of planets around it. Even with these tools, only a few exoplanets can be imaged directly, usually large gas giants, far from their stars, and often still warm from the heat of their formation. They appear as small, soft points of light, barely resolved, but undeniably present. These images are not sharp landscapes. They are not photographs of surfaces or clouds in detail. They are more like distant lanterns in the dark. Each point tells us that a massive planet orbits there, glowing faintly in infrared light, carrying its own moons, its own storms, its own long seasons. Even when we cannot see any detail, the simple existence of these distant points of light confirms what our other methods suggest, that planetary systems are common and often quite different from our own. There is another subtle way that planets reveal themselves through light, a method that uses transits not just to detect planets, but to probe their atmospheres. This is called transit spectroscopy. When a planet passes in front of its star, most of the starlight is blocked by the planet's solid or liquid body, but a small fraction of that light filters through the thin layer of gas around the planet, its atmosphere. As the light passes through this gas, molecules in the atmosphere absorb specific colors, specific wavelengths, depending on their chemical structure. Water vapor, methane, carbon dioxide, sodium, and many other gases leave unique fingerprints in the spectrum. By comparing the spectrum of the star during a transit with the spectrum when the planet is not in front of the star, astronomers can detect these tiny differences. They can see the faint imprint of the planet's atmosphere superimposed on the star's light. From these imprints, we can infer the presence of particular molecules, estimate the temperature of the atmosphere, and even make guesses about clouds and hazes. The signal is incredibly small, often just a tiny change in how deep the transit appears at different wavelengths of light. But when we average many transits together, patiently stacking data over months or years, a pattern emerges, a spectral fingerprint of an atmosphere on a world many light years away. In this way, we have learned that some exoplanets have bloated, hydrogen-rich atmospheres, some are shrouded in thick clouds that mask their deeper layers, and some show hints of more complex chemistry. Though always with caution, always with the awareness that our models are still incomplete. The process is like listening to a distant, muffled voice, hearing only a few words clearly, and using those to infer the rest of the sentence. There is uncertainty, but there is also real information, enough to say that these worlds are not simple points of light. They are places with weather, with pressure, with winds and temperature gradients, all governed by the same physics that shapes atmospheres on Earth. Not every exoplanet announces itself with transits or easily measured wobbles. Many orbit at angles where they never pass between us and their stars. Many are too small, too far, or too faint to be detected individually. Yet even these unseen planets contribute to our understanding, because we can learn from statistics, from the patterns that emerge when we look at many stars at once. When a mission like Kepler stared at a patch of sky for years, it did not aim to detect every planet around every star. Instead, it aimed to detect a representative sample, just enough worlds to estimate how common different types of planets are. By counting how many transiting planets are found around stars of different sizes, and correcting for the fact that most planetary systems will not be oriented in a way that produces visible transits, astronomers can estimate how many planets the average star has, and how those planets are distributed in size and orbit. From these statistical studies, we have learned that small planets, between the size of Earth and Neptune, are far more common than giant planets like Jupiter. We have learned that compact systems with several planets in tight orbits are frequent, and that planetary systems often look quite different from our own solar system. We can also estimate how common planets in the so-called habitable zone might be, where temperatures could allow liquid water on a rocky surface. By modeling detection biases and extrapolating from the planets we do see, we arrive at the conclusion that many stars, perhaps even a significant fraction of Sun-like stars, host at least one roughly Earth-sized planet in a temperate orbit. These are not exact numbers. They are ranges, estimates, refined as more data arrives. But they paint a picture of a galaxy that is rich in worlds. A galaxy where planets are not exceptional curiosities, but common outcomes of star formation. Through all these methods, a theme emerges. We do not study exoplanets by seeing them directly in crisp detail. We study them through whispers in the light, through patterns in brightness, through small oscillations in spectral lines, through faint imprints in transit spectra, through the collective behavior of many systems analyzed together. It is a kind of astronomy that rewards patience, subtlety, and calm. The data arrives slowly, over months, over years, often over the lifetime of entire missions. Each measurement by itself may look insignificant, but when thousands of them are combined, the presence of a planet becomes clear, like ripples on still water revealing the passage of an unseen object beneath the surface. These variations in light and motion reveal the hidden worlds orbiting distant stars. From your quiet vantage point in the dark, you can imagine these measurements unfolding, graph lines slowly taking shape, points of data aligning into smooth curves, tiny shifts in spectral lines tracing out the mass and orbit of a world you will never visit. The process is delicate, unhurried, and almost dreamlike, yet the results are firmly anchored in physics, in the predictable behavior of light and gravity. Drifting here, in the calm between stars, you can feel how this kind of science aligns with rest. It does not demand quick reactions. It does not burst with sudden revelations. It unfolds like a slow tide, revealing more of the shore with each gentle wave. In this quiet unfolding, whole catalogs of planets have been discovered. From the first hot Jupiters found by radial velocity measurements, to the thousands of transiting worlds revealed by space telescopes, to the few directly imaged giants glowing faintly in infrared light, each method adds another layer of understanding. Each signal, no matter how faint, points to a real world, moving in an orbit shaped by gravity and time. And as you continue to drift in this calm, you can hold that image in your mind, a galaxy filled with stars, each one a system of gravitational relationships, each one likely hosting planets you cannot see, but can still know are there, because the light and motion of their stars carry quiet, measurable signs of their presence. The hidden worlds are not hiding in any intentional sense. They are simply too small, too faint, too distant. But with patience, with carefully designed instruments, and with the willingness to listen to very small whispers in the data, we have begun to bring them into our awareness. And as you rest here, surrounded by this gentle awareness, you are free to drift among them in thought, knowing that behind every soft dip in a light curve, behind every tiny wobble of a star, there is a planet following its long, steady path in the vast quiet of the cosmos. Drifting through the galaxy in thought, you begin to notice that not all worlds are alike. In fact, the more carefully we look, the more we realize that our solar system is only one possible arrangement, one example among many, a single configuration in a universe that seems to favor variety. Planetary systems are not stamped from a single mold. They are sculpted by gravity, by angular momentum, by the cooling of gas and dust, by collisions and migrations that take place over millions of years. What emerges from this long process is a rich spectrum of planetary types, some familiar, some unlike anything we had ever imagined before we began to discover exoplanets. Tonight, as you rest, you can imagine yourself gliding from one kind of world to another, each one a calm diorama in the quiet of space, each one governed by the same physical laws, yet expressing those laws in very different ways. The first kind of exotic world that drew our attention was the hot Jupiter. Before the first exoplanets were discovered, many astronomers expected that other systems would resemble our own, with small rocky planets near the star and massive gas giants far away. But the first planets found by the radial velocity method overturned that expectation. We began to detect massive planets, with masses comparable to or greater than Jupiter, orbiting very close to their stars. Sometimes in just a few days. Their orbital distances were a tiny fraction of the distance between Earth and the Sun, placing them in regions where the stellar radiation is intense, where temperatures soar to levels that can heat their atmospheres to thousands of degrees. These are the hot Jupiters, gas giants that have migrated inward, moving through the primordial disk, or through gravitational interactions with other planets, until they settled into tight, close orbits. Many of these worlds are tidally locked, showing the same face to their star at all times. One hemisphere bakes in perpetual daylight, while the other lies in eternal night. On the day side, the atmosphere can be superheated. Molecules may break apart into atoms, clouds can form from vaporized metals and minerals, and winds can race from the hot day to the cooler night side at speeds of many kilometers per second. On the night side, temperatures fall, molecules recombine, clouds condense, heat slowly radiates away into space. From afar, you can imagine a hot Jupiter as a softly glowing world, its atmosphere lit not just by reflected starlight, but by its own thermal emission. Currents and jets move unhurriedly from our distant vantage point, forming broad patterns in the gas. The extreme temperatures and winds become simple facts of climate, no more threatening than a storm seen from orbit, simply another way that physics expresses itself. The existence of hot Jupiters told us that planets can move significantly after they form, that orbits are not fixed early and forever, but can migrate inward or outward under the influence of gravity and disk interactions. This insight reshaped how we think about planetary system architecture and opened our minds to a wider range of possible configurations. Beyond the hot Jupiters, as the sensitivity of our instruments improved, we began to detect smaller planets, worlds whose sizes fall between that of Earth and Neptune. These are often called super-Earths and mini-Neptunes, and they appear to be the most common class of planets in the galaxy, strangely absent from our own solar system, but abundant around other stars. A super-Earth is typically thought of as a planet a few times the mass of Earth, with a radius somewhat larger than Earth's. It may be rocky, with a solid surface, perhaps with oceans or thick atmospheres, depending on its formation history and distance from its star. A mini-Neptune, by contrast, is a planet with a similar mass range, but possessing a substantial envelope of light gases like hydrogen and helium. This envelope inflates the planet, making its radius larger relative to its mass, and giving it a lower average density. When we plot the sizes of exoplanets, we see an interesting feature: a gap in the distribution of planet radii. There are many planets somewhat larger than Earth, and many planets somewhat smaller than Neptune, but fewer in the intermediate range. This pattern suggests that atmospheric loss processes, driven by high-energy radiation from the host star, can strip lighter gaseous envelopes from some planets, transforming what might have been a mini-Neptune into a denser super-Earth over time. In this quiet, drifting state, you can imagine a spectrum of these worlds. Some are compact, rocky, with high surface gravity, perhaps covered in thick atmospheres of carbon dioxide or nitrogen. Others are puffier, with deep gaseous layers, no solid surface at all, just increasing pressure and temperature as you descend. From a distance, they appear as small points, but in your mind's eye, you can picture the transition from solid rock to deep gas, from high density to low, all governed by the balance between gravity, composition, and stellar radiation. These worlds, so common in the data, remind us that our solar system's lineup is not typical, that nature often favors configurations that we do not see at home. Among the most extreme of all discovered planets are the lava worlds. Think of a rocky planet orbiting so close to its star that its surface temperature is high enough to melt rock. The substellar point, the region directly facing the star, can be hot enough to maintain oceans not of water, but of molten silicates. Liquid rock, shimmering and convecting, flowing slowly like a thick glowing sea. Worlds such as 55 Cancri E and the object often referred to as K2-141b are candidates for such environments. On these planets, the surfaces may be divided between a molten day side and a cooler, though still extremely hot, night side. Rock vapor can evaporate from the hot regions, forming a tenuous atmosphere composed of silicate gases. These vapors may travel on winds and then condense on the cooler side, where they can rain out as mineral droplets, completing a rock cycle analogous to the water cycle on Earth, but at far higher temperatures. From a peaceful distance, you can picture these worlds as dark spheres with a fiery crescent, the day side glowing like cooled lava in a volcanic field, the night side hidden in shadow. The brutal heat, the intense radiation, all become part of a quiet, predictable pattern. a result of their close orbits and the energy they receive from their stars. Even the violence of molten surfaces, when seen on planetary scales and long timescales, expresses itself as slow convection, as the gradual rise and fall of hot material, as cycles repeated over millions of years. Not all planets remain bound tightly to their stars. Some worlds are thought to drift freely through interstellar space, no longer gravitationally attached to any particular star. These are the rogue planets, likely born in planetary systems, but ejected through gravitational encounters or formed directly in collapsing gas clouds without ever being strongly bound to a star. In the vast darkness between stars, a rogue planet would receive almost no external light or heat. Its surface, if it has one, would be lit only by distant starlight and perhaps a faint internal glow. Yet even such a world may not be completely frozen and inert. If it retains internal heat from its formation, or from radioactive decay, or from tidal interactions with a surviving moon, it could host subsurface oceans beneath an insulating layer of ice. In that case, liquid water might exist far below the surface, protected from space by thick ice and warmed from within, a quiet ocean sealed in darkness, isolated yet persistent over long timescales. From your drifting position in the galaxy, these rogue planets are invisible, lost in the dark, but statistical models suggest that there could be many of them, possibly as numerous as the stars themselves. Each one follows a lonely path, yet its loneliness is peaceful, a steady coasting through a medium that offers almost no resistance, no drag, no friction, just the smooth geometry of its trajectory through the Milky Way's gravitational field. Then there are the ocean worlds, planets that may be covered entirely in deep global seas. On such a planet, there may be no continents at all, no exposed dry land, only water, stretching from pole to pole, with perhaps thick layers of high-pressure ice forming at great depths beneath the liquid layer. The pressure at the bottom of these oceans could be immense, far beyond what we experience in Earth's deepest trenches. Different phases of ice, denser and more compact than the ice found in a household freezer, could form under these conditions, creating a solid boundary between the liquid water above and the rocky mantle below. Depending on the amount of heat flowing from the interior and the energy received from the star, these oceans could host complex circulation patterns, with currents transporting heat from the equator toward the poles and from the surface toward the depths. In some scenarios, such ocean worlds might exhibit thin atmospheres with water vapor and possibly other gases. In others, thicker atmospheres could trap heat, moderating surface conditions. From afar, one can imagine a soft blue sphere, cloud bands curling above a continuous ocean, storms forming and dissipating over scales of weeks and months, all part of a stable hydrological cycle. Such worlds are interesting from an astrobiological perspective because water is a powerful solvent, and on Earth it is intimately connected with life. Yet the deep high-pressure ice layers could isolate the oceans from the rocky interior, affecting the availability of nutrients and shaping the potential for long-term habitability. These are scientific questions, still unresolved, but they do not disturb the calm picture. Instead, they add subtlety, reminding us that even worlds dominated by water can take many forms. A related but distinct idea is that of hycean planets, a term formed from hydrogen and ocean, referring to theoretical worlds that are larger than Earth, with significant hydrogen-rich atmospheres and deep liquid oceans rich in water beneath. In these models, the hydrogen-rich atmosphere acts as a powerful heat blanket, extending the range of orbital distances where liquid water could be stable at the surface. A hycean world could orbit closer to its star or farther away than a traditional habitable zone might suggest, and still maintain conditions that allow liquid water. The atmospheric composition, pressure, and cloud structure on such planets would likely be very different from Earth's. Skies might be thick with haze, colors shifted by the scattering properties of hydrogen and any trace gases. From the point of view of an observer in orbit, a hycean planet might appear as a smooth, slightly flattened sphere, perhaps with muted colors, its details blurred by the thickness of its atmosphere. Spectroscopic studies of such worlds, if we can obtain them, could reveal signatures of water vapor and perhaps of other gases that might be associated with biological or geological activity. Although any claims would require extreme caution, the possibility of such planets expands the range of environments we consider when thinking about life. For you, resting in this imagined journey, these worlds simply add another texture to the gallery, another quiet variation on how a planet can maintain liquid water and complex chemistry without needing to resemble Earth closely. Beyond these specific types, the diversity extends further to ice giants, carbon-rich worlds, and iron-dominated planets. Ice giants, like Uranus and Neptune in our own system, are composed largely of substances like water, ammonia, and methane, combined with hydrogen and helium. Their interiors may host exotic forms of matter, including superionic water, where oxygen atoms form a lattice and hydrogen ions move freely through it, conducting electricity under extreme pressures and temperatures. Exoplanet surveys have revealed many planets in the mass range of ice giants, often in orbits closer to their stars than Uranus and Neptune are to the Sun. These so-called warm or hot Neptunes may have partially stripped atmospheres or different internal structures, depending on their history and environment. Carbon-rich worlds are hypothetical planets formed in regions of protoplanetary disks with higher ratios of carbon to oxygen. If such a planet accreted large amounts of carbides, its mantle might contain significant carbon compounds, including layers of graphite or even diamond under high pressure. An iron planet, on the other hand, would be dominated by a massive iron core with only a thin silicate mantle and crust. The surface gravity could be very high, and the planet's density much larger than that of Earth. These possibilities arise naturally from the physics and chemistry of planet formation, varying with the composition of the disk, the accretion history, and the differentiation of materials as the planet cools. From a tranquil vantage point, you can imagine a sequence of these worlds lined up in space, one dense and metallic, another enriched in carbon, another wrapped in thick ices and gases. All of them obey the same rules of mass, density, and hydrostatic equilibrium, yet each one arrives at a distinct internal structure. What all of these worlds share, despite their differences, is the quiet regularity of their motion. Each one traces out an orbit around its star, or, in the case of rogue planets, around the center of mass of the galaxy. Some rotate quickly, with days shorter than a single Earth day. Some rotate slowly, with days that may stretch longer than their years. Some are locked in synchronous rotation, turning one face forever toward their star. But from the perspective of someone drifting in deep space, the differences in temperature, composition, and internal dynamics all become part of a calm continuum. A library of planetary outcomes produced by the same underlying laws. Each world is a quiet diorama, a three-dimensional display case of geology, atmospheric physics, and orbital mechanics. The fierce winds of a hot Jupiter, the molten seas of a lava world, the deep waters of an ocean planet, the lonely path of a rogue planet, the dense interior of an iron world, all become scenes you can visit in thought, observe from a safe, silent distance, and then drift away from, without disturbance. Your curiosity does not need to be sharp or demanding here. It can be soft, content to float from one possibility to another, taking in the diversity of outcomes that arise from the same cosmic ingredients. Hydrogen, helium, carbon, oxygen, iron, silicon, and a few other elements, combined in different proportions under different conditions, give rise to this entire spectrum of alien worlds. And as you rest with these images, feeling their variety, yet also their underlying unity, you can sense how the universe does not favor one type of world over another. It simply allows matter and energy to follow the rules of physics, and the result is a gallery of planets so broad that our classifications are only temporary guideposts. The diversity of alien worlds is not chaotic. It is structured, but spacious, leaving room for many outcomes we have not yet observed. In that spaciousness, your mind can wander, slowly, calmly, from one hidden world to the next, knowing that each one, no matter how extreme, follows its path in the same quiet, cosmic night. Imagine drifting in a slow orbit above a distant planet, not rushing, not descending, just circling quietly, letting the world turn beneath you. From this vantage point, the most striking feature is not the solid surface, but the thin film of gas that clings to it, its atmosphere. On Earth, we walk through air without thinking about it, yet even here, our atmosphere is only a fragile layer, a thin gradient of pressure and temperature, maintained by gravity, solar radiation, and the rotation of the planet. On distant worlds, the same basic principles apply, but the outcomes can be dramatically different. Skies can be thick or thin, clear or hazy, hot or cold, colored by molecules and clouds unfamiliar to our eyes. As you drift above these planets in thought, you can imagine their climates as slow, persistent patterns, shaped by the balance between starlight, thermal radiation, and the movement of gases across the globe. Every planetary climate begins with energy from its star. The amount of radiation a planet receives depends on its distance, on the brightness of the star, and on the angle at which the light arrives. Near a bright star, a planet can receive intense flux, raising its equilibrium temperature, causing its atmosphere to expand, driving vigorous circulation. Far from a dim star, the same kind of planet might receive only a faint glow, barely enough to keep surface volatiles from freezing, unless other sources of heat are present. The concept of energy balance is simple in principle. The planet absorbs energy from its star and radiates energy back into space in the form of infrared light. If absorption and radiation are in balance, the planet's average temperature settles into a relatively stable value, modulated by seasons, clouds, and internal heat. But the fraction of starlight a planet absorbs is not fixed. It depends on its reflectivity, its albedo. A bright world, covered in clouds or ice, reflects much of the incoming light back into space, absorbing less energy. A darker world, with oceans, rock, or thick, low clouds, absorbs more, warming more easily. Then there is the role of greenhouse gases. Molecules such as water vapor, carbon dioxide, methane, and many others can be mostly transparent to incoming visible light, yet absorb strongly in the infrared. They allow starlight to reach the surface or lower atmosphere, but impede the escape of thermal radiation, trapping heat and raising the surface temperature above the value one would calculate from radiation balance alone. On Earth, this greenhouse effect keeps our surface hospitable. On some exoplanets, strong greenhouse effects can create much hotter conditions, especially on worlds close to their stars, or those with thick atmospheres rich in infrared-absorbing gases. In your quiet orbit, you can imagine sliding from one world to another, feeling how small changes in distance, reflectivity, or atmospheric composition translate into large differences in climate. A planet slightly closer to its star, with a slightly denser greenhouse atmosphere, could cross the threshold into a runaway greenhouse state, while a similar planet slightly farther out, with less greenhouse gas, could be locked in a global ice house. These thresholds are not abrupt in a dramatic sense. They are crossed slowly, over long timescales, as volatiles evaporate, condense, or escape, as chemical cycles gradually shift the balance of gases. Around many exoplanets discovered so far, the host stars are cool red dwarfs, smaller and dimmer than our Sun. Because these stars are fainter, the habitable orbit range, where liquid water might exist on a rocky surface, lies much closer to the star, at distances where tidal forces are strong. Over time, these forces can synchronize the planet's rotation with its orbital period, so that it always shows the same face to the star. This is tidal locking. On such a world, one hemisphere is in eternal daylight, the star fixed high in the sky, or hanging permanently near the horizon, depending on location. The other hemisphere is in perpetual night, never receiving direct starlight. At first glance, this might seem hostile to stable climates. One could imagine the day side overheating and the night side freezing so thoroughly that the atmosphere collapses, with gases condensing onto the surface as ice. But global climate models suggest that if the atmosphere is thick enough, and if winds can efficiently transport heat, the distribution of temperature can be more moderate. Strong day-to-night winds can move warm air from the illuminated hemisphere to the dark one, while returning colder air at lower levels, creating a slow, planet-wide circulation loop. Clouds may form near the substellar point, where air rises, cools, and condenses. These clouds can reflect much of the incoming starlight, limiting the temperature at the surface below. On the night side, radiation escapes to space more readily, but if the atmosphere retains sufficient heat, and if there are greenhouse gases, the surface may remain above the condensation point for major atmospheric components. A particularly interesting region on such tidally locked planets is the terminator zone, the permanent boundary between day and night. Here, the star would always hover near the horizon, casting a gentle, endless twilight. The temperature might be more temperate, neither intensely hot nor deeply cold. This band could be a stable corridor where liquid water might exist, if other conditions are favorable. From your vantage point, you can imagine gliding above this twilight ring, watching clouds flow from day into night, watching winds curve and spiral as they attempt to even out the planet's thermal contrast. What sounds like a dramatic configuration becomes, over long timescales, a balanced dynamical system, with circulation patterns that repeat and evolve slowly, like a global, gentle heartbeat of the atmosphere. On many exoplanets, clouds form not from water alone, but from a wide variety of condensable substances, depending on temperature, pressure, and composition. On hot Jupiters and ultra-hot Jupiters, where atmospheric temperatures can reach thousands of degrees, clouds may consist of silicates, metal oxides, and other high-temperature condensates. Imagine clouds of tiny mineral particles forming at high altitudes, casting shadows on the layers below. Their presence affects the planet's albedo, its spectral signature, and its heat distribution. As temperatures rise even higher on the day sides of the most extreme worlds, some condensates may evaporate entirely, leaving cloud-free regions, while on the cooler night side, the same species condense into thick decks. The result is an atmosphere where cloud coverage varies drastically between hemispheres, with patchy structures near the terminator, and possibly bands or spots where atmospheric dynamics concentrate particles. On cooler exoplanets, different substances may dominate clouds. Methane-rich atmospheres can form hydrocarbon hazes. Titan in our own system is an example of this process, and similar outcomes are likely on exoplanets with comparable chemistry. Carbon monoxide, ammonia, and other molecules can also condense under appropriate conditions, producing layered cloud decks with distinct optical properties. From our remote perspective, we infer these cloud structures indirectly, through their influence on the planet's emission and reflection spectra, through phase curves that track brightness as the planet orbits its star. We do not see individual cloud shapes. We sense their global effect, their averaged presence. Drifting in orbit above such a world, in thought, you might imagine a softly glowing sphere, with bright regions where clouds reflect starlight, darker bands where deeper, warmer layers shine through, and a night side that radiates residual heat to space, modulated by high, cold cloud tops. In the calm of that image, clouds are not sudden storms, but long-lived features, expressions of the steady interplay between condensation, evaporation, and atmospheric circulation. Over long times, atmospheres are not fixed. They can gain and lose mass, especially in the intense environments close to stars. One important process is atmospheric escape. At the top of an atmosphere, molecules and atoms with sufficiently high speeds can exceed the planet's escape velocity, leaving the gravitational field and drifting into space. The distribution of molecular speeds depends on temperature. At higher temperatures, more particles occupy the high-speed tail of the distribution, making escape more effective, especially for light particles like hydrogen and helium. In addition to this thermal escape, there is escape driven by high-energy radiation from the star. Ultraviolet and X-ray photons can heat the upper atmosphere, creating an expanded, hot layer that can flow outward in a hydrodynamic wind, carrying away lighter components. On some close-in exoplanets, we have detected signatures of extended atmospheres, large clouds of hydrogen or helium trailing behind the planet, like a comet's tail. These observations suggest active mass loss as stellar radiation strips away outer layers over time. Additionally, charged particles in stellar winds can interact with atmospheric particles, transferring momentum and energy, enhancing escape in some regimes, especially when magnetic fields are weak or absent. Over millions to billions of years, these processes can profoundly reshape a planet's atmosphere. A mini Neptune with a modest hydrogen envelope may lose much of its light gas, becoming more like a dense super-Earth. A small rocky planet orbiting close to a volatile, rich young star may lose its primary atmosphere entirely, leaving behind a bare rock or a secondary atmosphere generated by volcanic outgassing. As you float above these worlds in your mind, you can think of atmospheric escape not as a sudden removal, but as a slow, continuous exhalation, a faint, persistent outward flow, barely perceptible over human lifetimes, yet decisive over astronomical timescales. The composition of an atmosphere, together with its pressure and the spectrum of the host star, determines the colors of the sky and the nature of sunrises and sunsets on that world. On Earth, shorter wavelength blue light is scattered more strongly by molecules in the air, making the sky appear blue during the day, while longer wavelength red light dominates sunsets and sunrises. On exoplanets, different combinations of gases and particles can lead to very different visual impressions. An atmosphere rich in sodium or potassium, with strong absorption in certain parts of the visible spectrum, can give the sky a yellow or orange tint, especially near the star's position in the sky. Atmospheres with abundant methane, like those on some giant planets and icy bodies, tend to absorb red light, leaving reflected light shifted toward blue and green hues. From orbit, such planets can appear deep blue, with subtle variations caused by clouds and hazes. Photochemical hazes, produced when ultraviolet radiation breaks apart molecules and allows them to recombine into complex organics, can give a planet a muted, brownish or golden appearance. These hazes can be optically thick, masking deeper layers and smoothing out contrast. Even more exotic situations exist on ultra-hot worlds, where atoms and ions dominate the high-temperature upper atmosphere. In those regimes, strong spectral lines can imprint distinct colors on the transmitted or emitted light. From your gentle orbital vantage point, you can imagine watching a star set behind the limb of an exoplanet. Its light filters through layers of gas, passing through molecules and hazes that select which wavelengths can continue. The result would be a gradient of colors, different from any sunset on Earth, but still governed by the same scattering and absorption physics, softly shifting from one tone to another as the star dips below the horizon. Each world has its own palette, its own pattern of light and color, derived from chemistry, temperature, and pressure profiles. These differences are subtle in the data, appearing as small variations in transit depths at different wavelengths. Yet in your imagination, they can unfold into coherent skies calmly arching above alien surfaces and oceans. Climates on exoplanets can span extremes that dwarf earthly experience. Some worlds are likely trapped in runaway greenhouse states, where increasing temperatures cause more greenhouse gases or vapors to enter the atmosphere, which in turn trap more heat, driving temperatures even higher. On such a planet, oceans, if they ever existed, could evaporate entirely, forming a dense, steam-rich atmosphere. Water molecules in the upper atmosphere would be broken apart by high-energy photons, with hydrogen escaping to space and oxygen engaging in further chemical reactions. Over long timescales, this process can desiccate a planet, leaving behind a dry surface under a thick, hot atmosphere dominated by heavy gases. At the other extreme, icehouse planets, with low greenhouse gas content or high reflectivity, can fall into global glaciation. Snow and ice increase albedo, reflecting more starlight, which cools the planet further, allowing ice to advance. This positive feedback can lead to snowball states, where nearly the entire surface is frozen. Yet, even on such worlds, internal heat from the planet's core and from radioactive decay can maintain regions of liquid water beneath ice. Subglacial lakes and oceans may persist, hidden under thick shells. In our own system, bodies such as Europa and Enceladus illustrate this possibility, and similar configurations are expected among exoplanets and exomoons. There are also planets that combine thick atmospheres with substantial internal heat, leading to conditions where the atmosphere is many times denser than Earth's and the surface pressure immense. On such worlds, winds near the surface might be slow despite strong pressure gradients, because the dense atmosphere resists rapid acceleration. Weather would still occur, but on different spatial and temporal scales, more like slow, large-scale circulation than sharp, rapid storms. From your resting place above these worlds, you can think of climate extremes not as chaotic events, but as alternative steady states. Each one is a solution to the same fundamental equations of fluid dynamics and radiation, given different boundary conditions. Runaway greenhouse, global icehouse, subsurface oceans, thick supercritical atmospheres, all are part of the spectrum of possible atmospheric equilibria. Each endures for long epochs, until some external forcing, such as changes in stellar luminosity, volcanic outgassing, or atmospheric loss, nudges the system toward a different state. When we speak of habitability, we often begin with the classical concept of a habitable zone, a range of distances from a star where a rocky planet with an Earth-like atmosphere could support liquid water on its surface. This concept is useful, but incomplete. Actual habitability depends on many interconnected factors, on atmospheric composition and pressure, on planetary mass and gravity, on the presence of magnetic fields that can shield the atmosphere from stellar winds, on the rate of volcanic outgassing, which can replenish greenhouse gases and maintain active geochemical cycles. The spectral type and activity of the host star also matter. A red dwarf star emits more of its energy at longer wavelengths than a sun-like star, and can produce powerful flares and bursts of high-energy radiation, which may erode atmospheres or alter their chemistry. Tidal forces can heat a planet's interior, especially in multi-planet systems where gravitational interactions maintain eccentric orbits. This tidal heating can sustain subsurface oceans or drive long-term volcanism. In some cases, tidal heating may enable liquid water in regions outside the classical habitable zone, where stellar radiation alone would be insufficient. Energy sources for potential life need not be limited to direct starlight. Chemical gradients at the interface between rock and water, or between different layers of the atmosphere, can also drive metabolic processes, as seen in certain terrestrial microbes. From this broader perspective, habitability becomes a multi-dimensional space, not just a ring around a star, but a region in parameter space defined by energy sources, solvents, and chemical availability. As you float among these possibilities in your mind, you can imagine a map of conditions, with different classes of worlds occupying different regions. Some zones support stable surface oceans, some host deep subsurface seas under ice, some present transient habitable conditions that last only for limited epochs. Our observations are still sparse. We detect broad atmospheric traits on only a small fraction of known exoplanets. Yet even this limited view shows that climates, skies, and potential habitability are diverse and cannot be fully captured by simple one-dimensional distances from stars. In the quiet of this realization, you can let the complexity become soothing, not overwhelming. Each new parameter, each new nuance, is another way the universe allows worlds to differ. Another degree of freedom in the cosmic design, and all of it, from the simplest energy balance to the most intricate climate feedback, unfolds slowly, over times far longer than a human life. Worlds take their time to warm, to cool, to lock into rotation states, to condense clouds, to lose their atmospheres, to accumulate greenhouse gases. In that unhurried evolution, there is room for you to rest, to breathe slowly, and to drift through the gallery of alien atmospheres. Watching light scatter, watching clouds form and dissipate, watching climates settle into their long, enduring patterns, in the vast, gentle darkness between the stars. As you continue to drift in thought among these distant worlds, another question begins to rise very gently in the background. If planets are common, if atmospheres are common, if oceans and ice and clouds are scattered through the galaxy, then where, if anywhere, might life arise in all of this? Not as a sudden revelation, not as an answer shouted across the void, but as a quiet possibility, a question that unfolds slowly, like a long, deep breath. On Earth, life is intimately tied to chemistry and energy, to molecules interacting in liquid water, to flows of energy that move from one place to another, from hot to cold, from light to dark. These patterns are not unique to Earth. They arise wherever physics allows gradients of temperature, of chemical potential, of radiation. Life, as far as we know, needs at least three broad ingredients: a solvent, most likely a liquid that can carry molecules, allowing them to meet, react, and separate again; a source of energy, not too violent, not too weak, just strong enough to drive reactions, to push systems away from simple equilibrium, creating ordered structures that can store and process information; and a set of building blocks, atoms and simple molecules capable of forming more complex structures, capable of constructing membranes, catalysts, and informational polymers. On Earth, water plays the role of solvent. It is abundant, chemically versatile, liquid over a wide range of temperatures under suitable pressure, and capable of dissolving many kinds of molecules. Carbon serves as the main structural element, forming long chains and complex three-dimensional frameworks. Nitrogen, oxygen, phosphorus, sulfur, and various metals provide additional functionality. Energy flows from sunlight, from chemical gradients in rocks and oceans, from geothermal heat, and from redox reactions at interfaces where different chemical reservoirs meet. In principle, a similar combination of solvent, elements, and energy sources could arise elsewhere. Water is formed easily in many astrophysical environments. Carbon is abundant. Rocky planets and icy moons can host both solid surfaces and internal oceans. Stars emit a range of light, and geological processes create chemical gradients. So when we look out at exoplanets, we are often asking a quiet question, not only whether they are present, but whether they might host these conditions, whether somewhere among them there might be chemistry that has learned to persist, to replicate, to evolve. To search for life from afar, we cannot directly sample rocks or oceans on exoplanets. Instead, we look for signs in the light that reaches us, for patterns in atmospheric composition or in reflected spectra that are difficult to explain through non-biological processes alone. These signs are called biosignatures. One kind of biosignature is a chemical imbalance, a persistent state of atmospheric disequilibrium, where gases that should react with each other and disappear are instead maintained together over long times. On Earth, the combination of abundant oxygen and methane in the atmosphere is an example. Oxygen is highly reactive, and methane is easily oxidized. Without continual replenishment, they would not coexist at their observed levels for long. However, biology on Earth constantly produces oxygen through photosynthesis and methane through microbial metabolism and other processes. The atmosphere is therefore kept in a state that reflects continuous biological activity. If we were to see a similar kind of persistent disequilibrium on an exoplanet, with certain combinations of gases that resist simple abiotic explanations, it could be a hint, not proof, but a hint, that something active is maintaining that imbalance. Other potential biosignatures include nitrous oxide, certain sulfur compounds, or more complex organics in trace amounts, always evaluated in the context of planetary conditions, stellar type, and likely geochemical cycles. We can also search for surface biosignatures. For example, on Earth, vegetation affects how the planet reflects light. There is a characteristic change in reflectivity at certain near-infrared wavelengths, sometimes called a red edge, because plant leaves strongly absorb visible light, but reflect more in the near-infrared. If a distant observer measured the integrated spectrum of Earth as it rotates, they could, in principle, see this feature vary with time, as continents with vegetation rotate into and out of view. Some researchers have proposed that analogous features could arise on exoplanets with widespread photosynthetic life, perhaps shifted to different wavelengths depending on the star's spectrum and the pigment molecules that evolved there. All of these indicators are subtle. They are not single, unmistakable lines in a spectrum, but combinations of features, context-dependent patterns, requiring careful modeling and multiple hypotheses. In your gentle drift through this topic, you can think of biosignatures as whispers layered onto the already faint signals of exoplanet atmospheres, patterns that ask to be interpreted with humility, aware that non-biological processes can mimic many of them, but also open to the possibility that some patterns may eventually defy abiotic explanations. Beyond biosignatures, there is the idea of technosignatures, signs not just of life, but of technological civilizations. These could include narrowband radio emissions that stand out from natural background noise, coherent optical pulses from powerful lasers, or unusual patterns of infrared radiation associated with large structures that capture and re-emit stellar energy. For instance, a very advanced civilization might build large arrays of energy-collecting structures around its star, partially enclosing it and capturing a significant fraction of its light. Most of that energy would eventually be radiated away as waste heat, potentially producing an infrared signature that deviates from what we expect for a normal star. Alternatively, transit light curves of stars could, in principle, show shapes inconsistent with planets or natural debris, if large artificial structures passed in front of the star. So far, our searches have not found convincing evidence of such technosignatures, but they have only scratched a small portion of the possible parameter space. There are many frequencies, signal types, and timescales that we have not yet explored deeply. In the calm of this exploration, you can see techno-signature searches as a small, thoughtful extension of the broader question of life. Not a frantic hunt, but a patient listening for signals that may or may not exist within a galaxy that is mostly quiet at our current sensitivities. When thinking about life elsewhere, the nature of the host star matters deeply. Stars differ in mass, temperature, spectral output, and magnetic activity. A massive star burns bright and hot, emitting intense ultraviolet radiation, but lives for only tens or hundreds of millions of years, a relatively brief window for complex life to evolve. Smaller, cooler stars like red dwarfs emit less total energy, concentrated at longer wavelengths, but can remain stable for tens of billions of years, providing extremely long potential time spans for biological evolution. However, these same small stars can be magnetically active, especially when young. They can produce frequent flares and bursts of charged particles, which might strip atmospheres from close-in planets, or repeatedly bombard their surfaces with high-energy radiation. The habitable zones around such stars lie very close in, where tidal locking is common. As you drift in thought around a red dwarf world, you can imagine a planet with one hot side, one cold side, and a twilight band in between, all subjected to occasional flares that brighten the sky with energetic emissions. Whether such environments are favorable or hostile to life is still an open question. Some models suggest that atmospheres can survive, especially if they are initially thick or if planetary magnetic fields shield them. Others indicate that prolonged stellar activity could erode atmospheres away. Around more sun-like stars, the habitable zone lies farther out. Planets there can rotate more freely, with day and night cycles, and a balance of ultraviolet and visible light similar to what Earth experiences. Each type of star therefore frames a different context for habitability, a different balance between long lifetimes, energy availability, and atmospheric stability. From your calm vantage point, you can imagine rows of stars along the main sequence, from hot blue ones to cool red ones, each surrounded by potential planetary systems, each offering a different template for how life could emerge, or fail to. Within and beyond the classical habitable zones, water can exist in many forms, not only on the surface, but also in subsurface oceans beneath ice. In our own solar system, moons such as Europa, Enceladus, and possibly Titan provide examples. They host icy shells, with evidence for liquid water oceans below, maintained by tidal heating and internal energy sources. If such configurations are possible here, they are likely to be possible in exoplanetary systems as well, not only on moons but potentially on small planets far from their stars, or even on rogue worlds heated from within. In these subsurface oceans, sunlight might be absent, but chemical energy could still flow. From interactions between water and rock at the seafloor, from hydrothermal vents, from gradients in redox chemistry. On Earth, microbial communities thrive near deep-sea vents, drawing energy from chemical disequilibria rather than direct light. This tells us that biology does not require a bright sky, only a suitable solvent and a steady source of chemical-free energy. Thinking of this, you can imagine many hidden oceans scattered through the galaxy, dark, sealed under ice, quietly circulating for millions or billions of years. Perhaps some are sterile, perhaps some host only simple chemistry, and perhaps a few have crossed the threshold into true biology. From a distance, these worlds show little on their surfaces. They look like cold, icy spheres. But beneath their shells, in conditions shielded from radiation, there may be warm, stable environments, their status as living or non-living unknown to us, at least for now. As we consider all these possibilities, we are confronted with a philosophical tension, captured by two broad viewpoints. One viewpoint suggests that life may be common. Even if the emergence of life from non-living chemistry is rare on any individual planet, the sheer number of planets and moons in the galaxy might make living worlds numerous. In this view, given enough time and enough environments, chemistry finds pathways to self-replication and evolution more often than not. The other viewpoint, sometimes called the rare Earth perspective, emphasizes the many contingencies that shaped Earth's history. The specific combination of planetary mass, composition, orbital stability, moon formation, plate tectonics, magnetic field, and long-term climate regulation. It suggests that while simple microbial life might be widespread, planets that support long-lasting complex ecosystems and eventually technological civilizations, may be extremely uncommon. Our current data are not sufficient to decide between these pictures. We have only one confirmed example of life, and no confirmed examples elsewhere. The galaxy could be brimming with microbial worlds, yet nearly silent technologically. Or life could be rare at every level, with Earth standing as an outlier, a statistical surprise in a vast ensemble of sterile planets. Or it could be that life arises fairly often, but tends to remain simple, or tends to fade out before reaching large-scale complexity. From your calm point of view, you do not need to resolve this. You can let both possibilities coexist, as hypotheses suspended in the quiet, awaiting more data. In this uncertainty, there is a kind of humility, a recognition that our perspective is still very local, that our instruments have only just begun to probe the atmospheres of distant worlds, and that our future observations may surprise us in ways we cannot yet predict. To move from speculation to stronger inference, we are building and planning instruments dedicated to studying exoplanet atmospheres in more detail and to searching for potential biosignatures. The James Webb Space Telescope, with its large mirror and sensitivity to infrared wavelengths, has already begun to measure the spectra of some exoplanet atmospheres, especially those of larger, warmer planets that produce strong signals. By observing transits and eclipses at multiple wavelengths, it can infer the presence of certain molecules, constrain temperature profiles, and search for clouds and hazes. For small, temperate rocky planets, the signals are much fainter and the task more challenging. Yet over time, with many observations, patterns may emerge. Future concepts aim to go further. Large space telescopes equipped with advanced coronagraphs or external star shades, designed to directly image Earth-sized planets around nearby stars, would be able to obtain spectra of their reflected light, separating the planetary signal from the glare of the star. With such spectra, we could search for combinations of gases in the atmospheres of truly Earth-like worlds, and perhaps detect hints of surface features through subtle variations in the light as the planet rotates. Ground-based extremely large telescopes, with mirrors tens of meters across, will also contribute, using high-resolution spectroscopy and adaptive optics to study exoplanets from the surface of Earth. All of these efforts share a slow, incremental character. They accumulate signal over many hours of observation, combine data from multiple transits or orbital phases, and carefully subtract noise and systematic effects. There is no single, sudden moment when the sky announces the existence of life elsewhere. Instead, there will likely be gradual accumulation of evidence, spectra that suggest certain gases, models that increasingly favor biological explanations over abiotic ones, ongoing debates, and refined observations. In that process, the search for life becomes not a dramatic chase, but a long, thoughtful conversation between data and theory, between observation and interpretation. As you rest with this, you can feel how well it fits the slower rhythms of the cosmos and the slower rhythms of sleep. The universe is in no hurry to reveal its secrets. Stars burn for billions of years, planets evolve over eons, atmospheres change in steps measured across geological ages. Our search for life is simply another pattern unfolding within that larger timescale, a gentle, persistent effort to listen more carefully, to see more subtly, to understand more deeply what kinds of worlds exist, and which of them may be alive in ways both familiar and profoundly different. And as you continue to drift, you can hold this question not as a tension, but as a comfort. Somewhere in the quiet, among the many hidden worlds that orbit distant suns, the conditions for life may already have been met, perhaps many times over. Whether or not we ever confirm it, the possibility itself is soothing. It reminds us that the universe is capable of more than rocks and gas and ice, that it can also host chemistry complex enough to wonder about its own origins. For now, you are free simply to rest with that thought, floating in the deep, soft darkness between the stars, while the search for life continues slowly, patiently, across the galaxy. Imagine that you can glide from star to star, not in a rush, not as a mission with schedules or fuel constraints, but as a quiet observer, drifting on a slow current through the galaxy. From this gentle motion, you choose 5 worlds to visit in thought, not as a tourist looking for spectacle, but as a scientist at rest, content to simply watch how physics, chemistry, and time have shaped each planet into something unique. First, you find yourself approaching a small, cool red star. Its light is softer than the sun's, shifted toward longer, redder wavelengths. It is quieter, less overwhelming, but steady, a constant ember in the dark. Circling this star is a planet about the size of Earth, a world known as Kepler 186f. Its orbit places it within the region where liquid water could, in principle, exist on its surface. If the right atmosphere is present, you drift into a slow orbit above it, and let the world rotate beneath you in your imagination. From high above, the star is smaller in the sky than the sun appears from Earth, but redder. The daylight on the surface would have a warm, deep tone, colors shifted by the star's spectrum. If this planet has land and ocean, its landscapes might be bathed in a dim, brick-colored glow near sunrise and sunset, and a muted amber light at midday. If life has ever evolved here, its photosynthetic pigments might adapt to the star's red, rich light. Perhaps plants, if they exist, would not be bright green. They might absorb more of the red and infrared photons, reflecting darker, subtler hues. From orbit, you might imagine continents with broad, twilight forests, their surfaces appearing almost black at certain angles, because they are soaking up as much of the available light as possible. Clouds would drift slowly above, white or slightly tinted by aerosols, modulating the amount of energy reaching the ground, shaping local climates into zones of relative warmth and coolness. We do not know whether Kepler 186f actually has oceans, or continents, or life. Our measurements so far tell us its size, its orbit, its host star, and little else. But even with this limited information, we can see that it sits in an interesting position. A rocky-sized planet in a temperate orbit around a long-lived red dwarf, bathed in light that is weaker and redder than sunlight on Earth, but stable over long timescales. As you float above it in thought, you do not need to fill in every detail. It is enough to feel how small changes in stellar type and orbital distance can produce a world with familiar dimensions, yet very different illumination, a different rhythm of day and night, and potentially different pathways for climate and biology. You drift slowly away, leaving Kepler 186f circling its star in silence, each orbit taking many Earth days to complete, each year a quiet repetition of the same, simple geometry. Your next destination is another red dwarf system, but this one is closer to us and hosts a remarkable family of compact worlds. Here, the star is small and dim, yet tightly orbited by several planets, packed into a space that would fit well within the orbit of Mercury in our own system. One of these planets, often labeled E in the sequence, occupies a position that makes it especially intriguing. This is TRAPPIST-1e. You ease into an imagined orbit above it and watch as it presents the same hemisphere toward its star at all times, tidally locked, turning once per orbit so that one side experiences eternal day and the other eternal night. From above the day side, you see the star fixed in the sky, perhaps high above the substellar point, its red light pouring down continuously, warming the surface and driving atmospheric circulation. Air heated beneath the constant star rises, flows outward, and eventually descends toward the night side, closing the loop, carrying warmth into the darkness, returning cooler air back toward the dayside region. Along the terminator, the narrow band separating day and night, the star hovers forever near the horizon, casting an unending sunrise glow. If you lower your imagined vantage point to a location along this band, you would see a sky where twilight never ends. Light scattering through the atmosphere would paint gentle gradients, from deeper reds near the star's position to muted blues or purples overhead, depending on the atmospheric composition. Temperatures here, in many climate models, could be more moderate than on the intense day side or the frigid night side, making this twilight ring a potentially stable corridor for liquid water, if the atmosphere is sufficiently thick and if greenhouse gases balance the heat flow. TRAPPIST-1e, like its siblings, is small, dense, likely rocky, possibly with water either on or below its surface. Our current data do not yet confirm oceans, but they do suggest a compact, Earth-sized world with an orbit that receives a level of energy not radically different from that of Earth. As you continue to drift above it, you might picture thin clouds forming where air is forced to rise near the substellar region, flowing slowly into the terminator band, breaking into filamentary structures as they encounter changing temperatures and winds. On the night side, beneath a starless sky, the surface could be lit only by starlight scattered through the atmosphere from the day side, or by faint auroras if magnetic fields and stellar winds interact. All of this is still uncertain, a collection of physically plausible scenarios rather than direct observation, yet the basic elements are sound: tidal locking, day-night contrast, heat transport, and the possibility of a stable, twilight climate zone. You let the image soften, leaving behind a mental picture of a world with an eternal sunrise band, circling a small red star in a tight, predictable orbit, its climate an interplay between radiation, rotation, and atmospheric motion. From this compact system, you drift outward to a different kind of world, larger than Earth, wrapped in a thick gaseous envelope, and possibly covering a deep, global ocean. This is a planet known as K2-18b. It orbits a relatively cool star, in a region where the amount of energy it receives could, under some conditions, support liquid water somewhere within its structure. Measurements suggest that its size and mass place it between Earth and Neptune, too large to be a purely rocky Earth twin, yet too small to be a gas giant like Jupiter. Its density indicates that it likely possesses a substantial hydrogen-rich atmosphere, perhaps overlaying an ocean or a mixture of high-pressure ices and liquid layers. This combination has led to the idea that K2-18b might be a hycean-type world, with a deep, water-rich layer and a hydrogen-dominated atmosphere above. As you slide into your imagined orbit, you see a planet somewhat larger than Earth, its limbs softened by a thick, hazy atmosphere. Clouds may form at high altitudes, composed of water droplets or other condensates depending on the temperature and chemistry. If you think about the vertical structure, you can imagine a gradual transition from the low-pressure upper atmosphere, down through denser layers, into regions where pressure and temperature could allow liquid water, even if the surface pressure is much higher than what we experience on Earth. At certain depths, water might exist in supercritical states, where the distinction between liquid and gas becomes blurred. Below that, the immense pressures could stabilize exotic ice phases, forming a dense, solid boundary over any rocky core. Spectroscopic observations have hinted at the presence of molecules such as water vapor in the atmosphere of this world, and possibly other compounds, though interpretations are still under study, and alternative explanations must be carefully evaluated. From your peaceful, distant vantage point, you can think of K2-18b as a layered system, a quiet stack of gases, liquids, and solids, all arranged by gravity and thermodynamics. Winds move heat around the planet. Clouds form and dissipate. Molecules continuously collide and react. Whether life could exist in such an environment is an open question. The pressures and temperatures at certain levels might be compatible with complex chemistry, but the dense hydrogen atmosphere and potential lack of a solid surface present a very different context from Earth. Here, the idea of a habitable environment becomes more abstract. Perhaps niches exist in intermediate layers, where conditions are stable and energy gradients are available. You do not need to decide. You simply allow the possibility to rest in your thoughts, a calm, unresolved point in the spectrum of planetary types. The planet continues its orbit, a steady, elliptical path, while its atmosphere slowly changes over long timescales, shaped by stellar radiation, internal heat, and chemistry. Next, you drift toward a world that is almost the opposite of a temperate hycean candidate, a planet so hot that metals can vaporize in its atmosphere, a gas giant circling its star at a distance so close that its year is measured in only a few Earth days. This is an ultra-hot Jupiter, often referred to as WASP 121b. In your imagined orbit, you find yourself looking down at a world locked in a tight dance with its star. The planet is tidally locked, with a permanent day side blasted by intense radiation, and a night side that, while still extremely hot by terrestrial standards, is much cooler than the hemisphere facing the star. On the day side, temperatures can reach values where many common molecules break apart into atoms and ions. Water vapor can dissociate. Metals like iron and magnesium can exist partially in gaseous form. The upper atmosphere may host a thermal inversion, a stratosphere where temperature increases with altitude, due to absorption of the star's energetic radiation by certain molecules or ions. From a distance, the day side might glow brightly in infrared wavelengths, its spectrum dominated by atomic and ionic features rather than molecular bands. As you imagine sliding around to the night side, you would see a different regime. Here, the lack of direct stellar radiation allows temperatures to fall. Molecules can recombine, condensates may form, perhaps leading to clouds of exotic materials. Strong winds, driven by the day-night temperature contrast, circulate gas from the hot hemisphere to the cooler one and back, forming a global pattern of jets and waves. This circulation redistributes heat, blurring the sharpness of the day-night boundary, but not eliminating the contrast entirely. Observations of this world have provided phase curves, measurements of brightness at different orbital phases, showing how its emission changes as different longitudes rotate into view. From your quiet perspective, you can think of WASP 121b as a laboratory for extreme atmospheric physics, where processes we study under controlled conditions on Earth play out naturally on planetary scales. Chemical bonds breaking and reforming, clouds condensing from materials that are solid metal or mineral at Earth-like temperatures, winds moving at high speeds through a deep compressible fluid envelope. Despite the violence implied by high temperatures and fast winds, the overall picture, from afar, is slow and regular. The planet maintains its orbit, its tidally locked rotation, and its general atmospheric structure, over timescales far exceeding any storm or wave. You drift onward, letting the glow of this ultra-hot world fade behind you. Finally, you turn your attention to a smaller, but intensely heated rocky world, a planet that has become a symbol of lava worlds, circling so close to its star that its surface may be partly molten. This is 55 Cancri E. It orbits a bright star at a distance much smaller than that between Mercury and the Sun, completing a full orbit in less than a few Earth days. In your mental orbit above this world, you see a planet that is likely tidally locked as well, with a day side in constant view of its star and a night side that never sees sunrise. On the day side, surface temperatures may be high enough to melt rock, forming vast regions of molten silicate, a magma ocean that could occupy a significant portion of the hemisphere facing the star. Above this molten surface, elements and compounds from the rock can evaporate, forming a tenuous atmosphere made of rock vapor, sodium, silicon monoxide, and other species, depending on the exact composition of the crust. Winds can carry this vapor toward cooler regions. In the twilight and night side zones, temperatures drop, allowing some of these vapors to condense, raining out as mineral particles that eventually return to the surface. This creates a cycle, a rock cycle in the literal sense, not just tectonic recycling, but a continuous exchange between molten and gaseous rock, driven by the day-night temperature gradient. There are models that suggest different internal compositions for 55 Cancri E. Some propose it may be particularly rich in carbon, potentially allowing diamond-bearing layers under high pressure, though this remains speculative. From your tranquil vantage point, you focus less on the specific mineralogy and more on the clear fact that this world exists in a regime where volcano-like conditions that on Earth would be local events are instead global, permanent features. Yet even this extremity is not chaotic when viewed on planetary scales. It is a steady state, a configuration maintained by the balance between incoming stellar radiation, radiative cooling to space, and the physical properties of silicate materials. The magma ocean churns slowly, convecting heat from the interior and from absorbed starlight. The rock vapor atmosphere waxes and wanes with local temperatures. The night side possibly hosts solidified crust, cracked and remelted along its boundary with the hotter regions. As you drift above, you can picture a dark sphere edged by a glowing crescent of molten rock, its light flickering slightly as convection brings hotter material to the surface, then hides it again. No life as we know it is expected here. The conditions are far beyond the range of known biology, yet the world is still a valuable part of the planetary gallery, demonstrating how close-in orbits and stellar flux can transform a rocky planet into something that is more furnace than familiar landscape. These 5 worlds, Kepler 186f, TRAPPIST 1e, K2-18b, WASP 121b, and 55 Cancri E, are only a small sample of the thousands of exoplanets we have discovered. Each one illustrates a different combination of mass, composition, orbit, and stellar environment. Each one represents a particular solution to the equations of gravity, thermodynamics, and radiative transfer. From your quiet journey among them, you can sense both their diversity and their unity. They are all products of the same physical laws, played out under different initial conditions and histories. Some may host gentle climates and stable oceans. Some exist as deep gas envelopes or water-rich layers under hydrogen skies. Some are blasted by intense radiation, glowing fiercely in infrared. Some are partially molten, their surfaces turned to seas of rock. They all move through the same cosmic dark, bound to their stars by gravity, or drifting freely in the interstellar medium. As you let these images settle, you do not need to hold every detail clearly. It is enough to know that the galaxy is filled with such worlds, hidden, yet real, each one following its slow, enduring path in the vast, quiet expanse between the stars. As you drift through this quiet gallery of distant worlds, it is natural to wonder how clearly we will someday see them, not just as points of data, but as fully characterized planets, with measured atmospheres, maps of clouds, and perhaps even rough hints of continents and oceans. The tools we use now are powerful, yet they are only the beginning. The next generations of telescopes and instruments are being designed precisely to deepen this view, to turn faint whispers into clearer signals, to let us study other worlds with a level of detail that today feels almost out of reach. You can imagine all of this from your calm position between the stars, watching humanity quietly prepare new ways to look outward, each step patient, each advance another small improvement in our ability to read the light of distant planets. In orbit around Earth, large space telescopes will continue to play a central role. You can picture a future observatory, a successor to the current generation, designed specifically with exoplanets in mind. One concept carries the name Habitable Worlds Observatory. Its purpose, in broad terms, would be to directly image Earth-sized planets around nearby sun-like stars, and to obtain spectra of their atmospheres. To do this, such a telescope would need a large mirror to collect enough light from extremely faint planets. It would need extremely stable optics so that small variations in the wavefront of starlight can be controlled and corrected. And it would need sophisticated methods to suppress the star's glare, allowing the much dimmer planet to stand out. You can imagine this observatory floating in a stable orbit, perhaps at a gravitational balance point where the Sun, Earth, and spacecraft align, turning slowly as it alternately targets nearby stars, staring for long periods, integrating light photon by photon. From each target star, after careful processing and suppression of stellar light, a tiny dot of reflected planetary light might emerge, the signal of a world millions or billions of times fainter than its star. Simultaneously, on the ground, a new class of extremely large telescopes will come into operation. These instruments, with mirrors tens of meters across, will take advantage of Earth's atmosphere, but also need to overcome it. You can picture an enormous segmented mirror, high on a mountain, using adaptive optics to correct for the turbulence of air above it, small actuators constantly adjusting mirror segments, smoothing out the distortions introduced by pockets of warm and cold air. With this corrected view, these telescopes can produce very sharp images and spectra in narrow fields of view. They can perform high-resolution spectroscopy on starlight that has passed through exoplanet atmospheres, or on light from directly imaged giant planets. While ground-based telescopes cannot easily match the stability and clarity of space, they can offer huge collecting areas, gathering large numbers of photons in relatively short times, which is crucial for studying faint signals and for achieving very fine spectral resolution. Together, space-based and ground-based observatories will form a complementary network, each compensating for the other's limitations, each contributing different pieces of the exoplanet puzzle. Beyond single telescopes, future concepts also imagine arrays of instruments working together, especially in the infrared. In the mid-infrared part of the spectrum, roughly corresponding to thermal radiation from planets at temperate temperatures. The contrast between a planet and its star is more favorable than at visible wavelengths. Planets glow more brightly in their own thermal light, while stars, though still bright, are relatively less overwhelming. However, resolving a small planet close to a bright star at these wavelengths requires very fine angular resolution, which would mean extremely large single mirrors, far larger than is practical to build and launch. An alternative is interferometry, combining light from several smaller telescopes separated by large distances to achieve the resolving power of a much larger instrument. You can imagine multiple spacecraft flying in formation, each carrying a collector mirror, their positions controlled with great precision. They direct their collected light to a central beam combiner, where interference patterns encode information about the structure of the distant planetary system. By carefully adjusting the relative phases of the incoming light, such an interferometer can suppress starlight and enhance planetary light, creating a synthetic aperture much larger than any single mirror. From your calm vantage point, you can picture this as a kind of space-based choreography, multiple observatories moving in gentle formation, their relative distances maintained to within centimeters or even millimeters, while they drift hundreds or thousands of kilometers apart. The data they collect would not look like familiar photographs at first, but as complex interference patterns, these patterns would be transformed mathematically, reconstructed into images and spectra showing planets, their orbits, and their thermal emission. In the quiet of space, this dance of formation, flying, and interference would unfold slowly and precisely, each new configuration probing a different spatial scale or orientation, each observation adding new detail to our picture of other planetary systems. Suppressing starlight is one of the central challenges in directly imaging exoplanets, and two complementary technologies are being refined to meet it. Inside telescopes, coronagraphs sculpt the incoming wavefront of starlight, using masks and deformable mirrors to cancel or redirect most of the light from the central star, while allowing light from off-axis planets to pass through. This process requires exquisite control, because even small imperfections can leak starlight into the region where we are trying to see the planet. You can imagine a coronagraph as a carefully tuned optical instrument, a set of elements adjusting the amplitude and phase of light, creating a dark zone in the image where the star's contribution is greatly reduced, like casting a precise shadow over the star's position, but not over its surroundings. Outside telescopes, the concept of a starshade proposes a different strategy, a large petal-shaped screen flying tens of thousands of kilometers away from a space telescope, aligned so that it blocks the starlight before it even enters the telescope's aperture. From the telescope's perspective, the starshade appears as a dark silhouette perfectly superimposed on the star. Its shape is optimized so that diffraction patterns are minimized, resulting in a very clean shadow at the telescope's location. Planetary light, arriving from slightly different angles, is not blocked by the starshade and can enter the telescope for imaging and spectroscopy. You can visualize the starshade as a quiet companion spacecraft, moving slowly along lines between the telescope and different target stars, repositioning itself for each new observation, a dark flower-shaped disk contrasting against the distant light of the star it is hiding. Together, coronagraphs and starshades form a toolkit for extreme contrast imaging, transforming what is now a formidable problem into something that can be managed with enough precision, stability, and time. With these tools in place, the next goal is to measure exoplanet atmospheres in much greater detail, with the specific aim of detecting possible biosignatures and understanding climate and chemistry on a wide range of worlds. Spectral biosignature detection involves observing a planet's light at many wavelengths, then comparing the measured spectrum with models of atmospheres containing different mixtures of gases. At high spectral resolution, individual absorption lines and bands can be distinguished. Their depths and shapes depend on the abundance of the corresponding molecules, on temperature and pressure profiles, and on line broadening mechanisms. By fitting models to the observed spectra, we can infer the presence and approximate concentration of gases such as water vapor, carbon dioxide, methane, ozone, nitrous oxide, and others. However, no single gas is likely to be a definitive sign of life by itself. Many can be produced abiotically through volcanism, photochemistry, or mantle degassing. Instead, biosignature analysis looks for combinations of gases, or persistent disequilibria in atmospheric chemistry that are more naturally explained with continuous biological input. This requires comprehensive modeling, multi-species atmospheric simulations that track how gases are produced, destroyed, and transported in the presence of stellar radiation, surface processes, and possible oceans or ice. You can imagine a future where, for a nearby Earth-sized planet, we acquire multiple modes of data. Transit spectra showing absorption features as the planet passes in front of its star, direct imaging spectra of reflected light at different orbital phases, and thermal emission spectra measured at infrared wavelengths. Combined, these datasets could constrain both composition and climate, surface temperature distributions, cloud coverage, and possible seasonal variations might all leave subtle but measurable imprints in the light. From your restful perspective, this may feel like building a very slow, very careful portrait of a distant world, using photons collected over many years. From the planet's point of view, nothing has changed. It continues its orbit, its rotation, its weather and geology. From our point of view, we gradually refine our inferences, narrowing down which combinations of gases and surface conditions are consistent with the data and which are not. In some cases, a picture might emerge of a world with water vapor, a temperate temperature range, and atmospheric components that suggest an environment favorable for life, even if we cannot claim direct proof of biology. In others, we may find dense, carbon dioxide-dominated atmospheres, or desiccated airless rocks, or thick, reducing envelopes around mini-Neptunes. Each outcome informs our statistics, helping us understand how common or rare different atmospheric archetypes are around different types of stars. As observations become more precise, we may even begin to extract coarse information about surface patterns on some planets, not detailed maps, but hints of continents and oceans inferred from how brightness and color change over time. When a planet rotates, different surface regions come into view. If these regions have different albedos and colors, for example, dark oceans and bright continents, or vegetated areas and deserts, they will modulate the total reflected light that we see. By measuring the planet's brightness and spectrum as a function of time, and by tracking changes over many rotations, we can attempt to invert these variations, constructing low-resolution maps of surface types and cloud patterns. This process is called light curve inversion, or albedo mapping. From your vantage point, you can picture an exoplanet as a slowly rotating sphere, its surface divided into broad regions. Each region reflects a different fraction of incoming light, and with a slightly different spectral signature. As the planet turns, these regions pass through the illuminated, visible portion of the disk, causing small oscillations in the total light measured by our instruments. With enough signal and with careful modeling, we can reconstruct a crude map of which longitudes are brighter or darker, which wavelengths are more reflective in certain regions, and how these patterns change with time. Clouds complicate the picture because they add their own variability. But they also carry valuable information about climate and circulation. The resulting maps would not resemble high-resolution satellite imagery. They would be more like blurred, large-scale patterns, identifying hemispheric differences or broad continent-sized features. Yet even that would be a profound step, transforming distant planets from simple spheres with averaged properties into worlds with geography, with weather zones, with evolving patterns on their surfaces. You can imagine looking at such a reconstructed map of a nearby exoplanet, knowing that each feature, each brightness variation is inferred from tiny changes in the light curve, accumulated over many rotations, carefully disentangled from noise and instrumental effects. In the context of sleep, this process feels almost like listening to a soft, complex rhythm, extracting structure from gentle fluctuations, learning to recognize a planetary heartbeat in the light. Looking farther ahead, beyond telescopes and remote sensing, people also imagine missions that do more than observe from afar, missions that send small probes toward other star systems, even if their journeys take decades or longer. One concept involves light sails, very thin reflective structures attached to small payloads, accelerated by powerful laser beams or by sunlight itself, pushed to a fraction of the speed of light by continuous radiation pressure. You can picture a fleet of such small probes, each only a few grams or kilograms in mass, unfolding their sails near Earth, then being illuminated by intense laser light from a ground or space-based array. The pressure from the photons gradually increases their speed, accelerating them along trajectories toward nearby stars. Proxima Centauri, Alpha Centauri, and other close neighbors become reachable on timescales of a few decades, from the probe's point of view. Once they arrive, they could attempt brief, high-speed flybys of planets in those systems, taking images and measurements and transmitting the data back to Earth with compact radio or laser links. The data would take years to return, traveling at the speed of light across trillions of kilometers. By the time the signals arrive, the people who launched the mission might be older, and in some cases, new generations of scientists would be the ones to interpret the results. From your tranquil position in this imagined future, you can see these missions as extremely patient experiments, bridging timescales between human lifetimes and stellar distances. Each mission a long arc, from design and construction, through launch and cruise, to a brief encounter, and then a slow delivery of information back home. More distant dreams include larger interstellar craft, perhaps using advanced forms of propulsion, fusion, beamed power, or concepts not yet fully understood. These visions remain speculative, but they express a direction, a gradual shift from observing exoplanets only as distant dots of light toward at least some level of physical presence in other systems, however small or robotic at first. In all of this, one can see a quiet transition from being a species that only looks outward to one that eventually can visit, sample, and perhaps even interact with other planetary environments. For now, we are at the beginning of this arc. Our instruments are just strong enough to detect atmospheres on some exoplanets, to measure bulk properties, and to infer broad classes of worlds. In the coming decades, larger telescopes, more refined coronagraphs, possible star shades, and perhaps infrared interferometers will sharpen this view. Then slowly we may move toward direct imaging of Earth-sized planets in habitable orbits, spectral searches for atmospheric disequilibria, and rough maps of clouds and surface contrasts. Beyond that, if technology and will allow, we may send small probes pushed by light to sample the nearest systems directly. From your perspective as a quiet observer in this narrative, all of this unfolds gently. There is no rush, only a gradual expansion of capability, a slow unfolding of clarity. As our instruments grow more sensitive and our understanding of planetary physics becomes more complete, the hidden worlds of exoplanets will not reveal themselves all at once. They will come into focus gradually, planet by planet, spectrum by spectrum, light curve by light curve, and as they do, they will enrich the night sky, turning distant stars into known systems, each with its own family of worlds, each with its own climatic stories, its own geological histories, and its own potential for life. In that long, patient process, there is a kind of quiet optimism, a sense that the universe will allow itself to be known, not hurriedly, but steadily, in a way that matches the slow turning of galaxies and the deep timescales of planetary evolution. You can rest within that optimism, letting it settle over you like a soft blanket, knowing that while you sleep and while you dream, the work of understanding these worlds continues, calmly, methodically, with instruments circling Earth and sitting on mountaintops, collecting faint photons from distant stars. The future of exoplanet exploration is not a single event, but a long sunrise, light spreading slowly across a landscape of unknown worlds, revealing more detail with each passing moment, yet always leaving room for mystery, for unanswered questions, and for the quiet wonder that accompanies every new glimpse of the hidden planets beyond our time. Sun, imagine, for a moment, that you are no longer anchored to any single star, any single planet. You are resting in the quiet space between systems, where the light from many suns overlaps so faintly that it becomes a gentle, almost unnoticeable glow. Around you, spread across the dark, are countless worlds, most of them never seen directly by human eyes, most of them known only as small changes in starlight, as numbers in a catalog, as curves on a graph. Yet each of those worlds is real, solid or gaseous, icy or molten, bathed in radiation or wrapped in deep shadow. Each one follows its orbit faithfully, year after year, century after century, turning in a gravitational pattern that does not need to be watched or managed or corrected. Planets simply move. They respond to gravity and momentum, to the same basic laws that govern your own body, your own breath, the flow of blood, the beating of a heart. As you lie still, you can let that thought sink in. The universe is not a distant, separate structure. It is the larger context in which everything unfolds, from the smallest molecule in your cells to the largest orbiting worlds. In the darkness behind your closed eyes, you can picture the Milky Way as a wide, slowly turning disk of stars. Within that disk, almost every star has planets, rocky ones, gaseous ones, icy dwarf worlds, and objects that defy simple categories. Some orbit close to their stars, completing a year in a matter of days. Some circle far out in the cold, taking centuries to return to the same point in their path. Some carry thick atmospheres that trap heat. Some have only a whisper of gas above bare rock. Some hide oceans under ice, never lit by direct starlight. You do not need to keep track of all of them. You do not need to remember their names or their orbital periods. Instead, you can let them blur into a single idea. The idea that worlds are not rare at all, but common, a natural outcome of star and disk formation, an expected result of gas and dust cooling, clumping, and collapsing under gravity. Wherever there is a star, there is a chance for planets. Wherever there are planets, there is a chance, however large or small, for atmospheres, for oceans, for chemistry that might, under the right conditions, cross the threshold into life. This does not mean that life is inevitable, or that complex organisms must be everywhere. It simply means that the stage on which life could appear is vast, much larger than the narrow region around a single star. When you think of it this way, the universe begins to feel like a cradle of possibilities, a place where many experiments in planetary physics and chemistry are running in parallel, most of them unseen, most of them silent to us, but all of them unfolding according to consistent principles. Curiosity, in this context, is not an agitation. It is not a restless demand for immediate answers. It is more like a calm, steady light, a willingness to let questions exist for a long time without needing to force them into resolution. You can be curious about whether life exists elsewhere, without needing to know the answer tonight, or this year, or even in this century. You can be curious about what climates unfold on distant worlds, what clouds look like under red suns, what oceans are like on planets with higher gravity, what skies would appear under thick, hazy atmospheres. But you can hold that curiosity gently, the way you would hold a quiet object in your hands, turning it slowly, examining it from different angles, without squeezing, without clutching. As you breathe slowly, you may notice that curiosity and calm are not opposites. They can coexist. Your mind can remain open, interested in the structures of reality, while your body relaxes, muscles loosening, breath deepening, heart rate slowing. The universe is not asking you to solve it. It is not presenting you with a test. It simply exists and offers more detail, more clarity, as instruments, theories, and time allow. You are free to rest inside that process, to listen to these ideas as one might listen to the patterns of rain, not trying to remember every drop, only letting the overall sound guide you gently towards sleep. Think again of a single exoplanet, any one of the many you have drifted past in thought. Perhaps it is a quiet, temperate world, with an atmosphere that softens the transition between day and night. Oceans spread across part of its surface, reflecting its star in long, broken lines of light. Perhaps it is a gas giant, striped with winds that circle the planet without ever stopping. Clouds rise and fall, storms grow and fade, yet the overall pattern persists, set by rotation, heat flow, and angular momentum. Or perhaps it is a frozen sphere, far from its star, with a shell of ice that has not melted for millions of years, while deep below, internal heat slowly seeps outward, maintaining a hidden ocean at high pressure, in total darkness. Each of these worlds is complete, whether or not we ever detect it. Each has a set of physical conditions that are not right or wrong, not good or bad, simply different from those on Earth. The fact that you can imagine them at all, from a small room on a small planet, orbiting an ordinary star, is already remarkable. It shows that your mind can extend far beyond the scale of your immediate surroundings, tracing gravitational orbits, chemical reactions, and climate patterns on objects that you will never visit directly. That understanding itself can be a source of comfort, not because it makes you large, but because it situates you accurately, as a small, conscious part of a much larger, coherent whole. You are not separate from the cosmos you are thinking about. You are made of its materials, carbon forged in stars, oxygen created in earlier stellar generations, iron atoms that once flowed in the cores of massive suns. Your curiosity about exoplanets is, in a very literal sense, the universe learning about other parts of itself, matter that has become able to reflect, to model, to ask questions. Knowing this, you can let any sense of isolation soften. You are already connected, through physics and chemistry, to the same processes that shape those distant worlds. As you continue to relax, you might imagine yourself floating between stars, like a slow-moving seed carried by a gentle interstellar breeze. There is no urgency here, no need to choose a destination. You pass one system, and then another, each with its invisible collection of planets. You know some of them by name, most of them only as data, and an enormous number not at all. Yet the pattern holds, stars with planets. Planets with atmospheres or bare rock or ice or oceans, each one following quiet curves through space-time. You can let those curves simplify in your mind until all orbits become one smooth idea, a sense of continuous, unhurried motion, like a gentle, steady breath. Inhale, and you imagine drawing in starlight. Exhale, and you imagine releasing it back as soft infrared glow. The same energy flow that defines planetary climates, in a very real way, also passes through you, from the food you eat, from the sunlight absorbed by plants, from the warmth that your body radiates into its surroundings. There is a symmetry here, a quiet echo between the large and the small, between planets balancing radiation and atmosphere, and a single person balancing oxygen and carbon dioxide, rest and wakefulness, exertion and sleep. Sleep itself can be understood in this same calm, scientific way, as a biological process with functions and mechanisms. But tonight, you do not need to analyze it, you can simply let it happen. Like a natural transition from one state to another, planets turn from day into night, not to achieve anything, but because they spin. You move from waking into sleeping, not as a failure of attention, but as a necessary part of how your brain and body restore themselves. You have spent some time drifting among other worlds in your mind. You have considered their orbits, their climates, their possibilities for life, and the future instruments that might study them. Now those thoughts can begin to loosen. They do not need to be held in sharp focus. They can become softer images, scenes that fade in and out, as your brain transitions from structured reasoning to the freer, less constrained patterns of dreams. If a particular planet image lingers, that is fine. You can keep it as a gentle backdrop, a dimly lit horizon under a strange star, an ocean under a deep, hydrogen-rich sky, a ringed giant, or a twilight band on a tidally locked world. But you do not need to follow the details anymore. You do not need to track which molecules are in the atmosphere, or which telescopes will one day take spectra. You are allowed to let the science dissolve into mood, into a simple feeling of vastness, structure, and calm. The universe is large and full of hidden planets. They will continue to orbit their stars, regardless of whether you are awake or asleep. The instruments that search for them will continue to collect data, regardless of whether you are thinking about them or dreaming about something entirely different. For now, your only task is to rest, to let your thoughts slow, to allow your awareness to narrow, until it becomes a small, warm point, floating in a safe, dark space. Around that point, you can imagine the quiet infinity of other worlds, not as a demand for attention, but as a soft, supporting background. A galaxy of planets, turning silently, unhurried, each one a variation on the same simple rules, each one a reminder that the cosmos is stable enough and enduring enough for you to let go for a while. You can release the day, release the questions, release even the images of exoplanets, if you wish. Or you can keep just one thought, a very small one, that somewhere far away, a planet you will never see is turning toward its star, while another, on the other side of the galaxy, is turning away. Both motions are smooth, predictable, quiet, just like your breath in and out. Let that rhythm carry you now gently deeper into rest. While the hidden worlds continue their silent journeys, you are free to sleep, held within the same vast, calm universe.